Saxon's Trigonometry, Lesson 1, Section G, beginning on page 9, is about areas and sectors of circles. Before they get into circles, they do a quick review of the area of some other shapes. So if we have a square or a rectangle, how do we find the area? We multiply length times width, whether it's a rectangle or a square. If it is a square, then it's actually labeled side, side, so you can say side times side or the abbreviated side squared. What if we have a triangle? How do we find its area? This one is going to be labeled base, and there is another piece that needs to be labeled. But before I do that, let's do a quick review. If I take this rectangle and I cut it, I've created two triangles. So the area of this triangle is only half of this overall shape. So if it was in length times width to get its area, we're going to change this to base times something, and then we want half of it. So this should be jogging your memory as to the formula for the area of a triangle. It's half base times height, and the height is obviously drawn from a peak down to the base. And they show you there in the book on page 9 the right triangle, an acute triangle, and an obtuse triangle, and the three different ways in which they can give you the information for height. Height in a right triangle, this is the base, this is the height, is one of the sides. In an acute triangle, that's the one I just did here, we have the base and the height. In an obtuse triangle, this is the base, and the height has to come from the vertex, and so it's actually in an outside piece. So it can be inside it, it can be the side, or outside, just depending on the kind of triangle. Now, we move to the actual circles that they were talking about in section G. So we have the, and we didn't talk about perimeter of any of these, but you should remember that the perimeter is the distance around. So here it would be like length plus width plus length plus width. Here it would be side plus side plus side plus side, or 4 S's. And then for the triangle, you're adding up the 3 sides, no matter how they're given to you. In a circle, what is the special name for the perimeter? It is circumference. And how do we find the circumference? Well, every circle formula deals with pi, which is the 3.14, and that's its special symbol. So pi times diameter, or it can be pi, 2 pi r, because the coefficient, the number should come first. So is the diameter, which is all the way across through the center, from the center out is considered a radius, and that would be the same this direction, so you can see why the diameter is the same as 2 radiuses, therefore it's the same formula. Now for area of a circle, you need pi times radius squared. And if you do not, for whatever reason, have those formulas memorized, you most definitely need to know them. We will use them an awful lot. All right, now at the very bottom of page 9, they talk about some terms that I have not quite said yet. This dot in the center is the center of the circle. Yes. If I create an angle inside, then this piece that I cut of the circumference is called the arc of the circle. And there is the central angle, which is the measurement of whatever angle is in or close to the center. So if this is 10 degrees, then its arc that it cuts will also represent 10 degrees. Now, I realize that they look very different because on the arc that's a lot wider, but that is just a mathematical rule that whatever it cuts, it's the same in measurement. This is a much tighter circle technically than this one, but the distance that is cut is still identical. Now on to page 10. I can also be asked to find the area of the sector. So what is the sector? So if I picture my circle as a pizza, the sector is the slice of the pizza, this part. And so it's asking us to find the area of basically a triangle, except that it's not, because that side is curved. So what we do is we find the area of the entire circle, which would be pi times radius squared, and we multiply that with only the part we wish to keep. How many degrees is the part we're trying to keep? 10 degrees out of how many is the entire circle? 360, and doing that, we'll find the area for the sector. And if we are actually doing this with numbers using the pi symbol on our calculator, however we're doing it, we need to make sure that in our answer for areas, we have like inches squared, feet squared, centimeters squared. Whatever it is for area is always squared. And basically that's because we've taken two sides and we've multiplied them. You see there is an actual example 1.1 on page 10, and it says the measure of the central angle of the unshaded sector is 126 degrees, and it's labeled in the picture. The radius of the circle is 2 times root 5 inches. Find the area of the shaded region of the circle. So we are going to find the area of the entire circle. So that is going to be pi times our radius squared, and it told us our radius was 2 root 5 or radical 5, and that needs to be squared. Then we need to reduce it down to only the amount of the circle it wants, and it wants the shaded region. So the unshaded is 126. We need to do 360 minus, because that's the whole circle, minus the 126. And again, faster on your calculator to do that. So 234 degrees is what we want out of 360. And then we're going to do that probably on our calculator. But I can also remind you that when you do 2 squared, you turn it into 4, and radical or root 5 times itself is just 5. So we're going to have 20 pi, and then this 234 over 360 can be reduced. But since in the answer it's, well, no, they left it with pi. So if you do that on the calculator, do 20 times 234 divided by 360, and that should give you 13. And then the pi symbol is still there. And this was originally in meters. And as I said, for area, make sure that is meters squared. And then I typically will box my answers, and you'll see that on any of the answer keys that you use with me. The last section, H, beginning on page 10, is a concept review problem. So it wants us to talk our way through the next several examples. Example 2 is on the very bottom of page 10. Let x and y be real numbers. If they don't clarify that wording, then I could be dealing with imaginary things, which they don't want us getting into anytime soon. So they will always clarify that x and y are real numbers. X is greater than 0. So what does that mean? My x numbers have to be positive numbers if they're greater than 0. Y is less than 0. So that tells me that my y numbers must be negative numbers to be less than 0. So then in the question, it's asking you to compare A and B as they're listed. If A is the larger concept, my answer will be A. If B is the larger concept, my answer will be B. In this book, there are 2 other implied but never said answers. C would be they are the same answer, and D would be there is not enough information provided for me to determine that A or B is bigger. So if in A I have a positive and I'm adding to it a negative, is that guaranteed to be bigger than a positive minusing a negative? Well, let's think our way through that. If I have a positive and I subtract a negative, probably going smaller. If I have a positive and I am, oh wait, I'm sorry, that one was a plus. If I have a positive and I'm adding a negative, I'm probably making it smaller. If I have a positive and I'm subtracting a negative, what happens when I subtract a negative? Oh, that turns it into an add. So I'm definitely going to be adding here. So whatever the numbers for A and B would be, this being an addition rather than a subtraction type of problem, because that's what it is when I'm adding the negative, B is going to be the concept that is always going to land to be bigger. Okay, example 3, page 11. Let x and y be real numbers. Again, they have to state that. If x falls between 1 and 6, and y falls between 1 and 6, what happens when I, in A, subtract them, x minus y, and in B, I do y minus x? Well, here's my problem with that. I know that my numbers are between 1 and 6 for both. So depending on whether x is bigger or y is bigger, my addition might be, A might be bigger, my subtraction, I'm subtracting in both cases. A might be bigger or B might be bigger. It just depends on which numbers are chosen. So do I have enough information to determine just based on what I was given? I don't. So this one is the implied D that is never listed but is allowable. Example 4. Given two intersecting lines with angles as they are marked K, L, M, and N, compare in A, K plus L plus M, and in B, 180 minus N. So, in this intersection, this is my M, this is L, K, and N. So for A, it asked me K, L, and M all being added together. So that's like 360 minus whatever N is would be the sum of all three of those. It's definitely an obtuse angle. Now let's compare. B says 180 minus N. Well, 180 represents a line, not a circle. So a line minus N is definitely going to be smaller than implying a circle. So I'm fairly certain that A is always bigger. Example 5 at the bottom of page 11. Given this diagram with segments Z, W, and XY being parallel, compare the area of the two given triangles. Okay. That needs to be a little longer there. Okay, this one and this one are forming the triangles. This is the Y, W, X, and the Z. And it wants us to compare WXY, WX. Okay, so this bottom one compare to ZXY, this bottom one. So we're comparing this bottom one to this bottom one. All right, and let's see. Areas we know are half base times height. The height is the same between these two segments and they're parallel, so that's my indication for sure that that height is the same. And the base is the same, shared in both those triangles. So if half the base times the height, if the base is the same and the height is the same, then their areas must be the same. So we are using the implied C for that answer.